Okay, our next presenter is MJ Riches. She is a third-year PhD student in chemistry, and she knew she wanted to study plants after the Hyde Park fire destroyed her grandfather's tree farm. She considers her research to be very multidisciplinary, combining analytical chemistry, atmospheric chemistry, and plant physiology. With her degree, she hopes to act as a liaison between the environmental chemistry community and the public to make policy-inspiring science more accessible to all. The title of her presentation today is A Plant's Role at the Crossroads of Climate Change.
We are at the crossroads between climate change and climate recovery. The world as we know it is at stake. Everything from California beaches to coffee and cocoa, from ocean acidification to breathable air. We tend to imagine the climate, the atmosphere, as something which surrounds us, when in actuality it is integral to every aspect of our lives. Which is why it should be alarming that the United Nations has given us 2 decades to get back on track concerning our emissions, or we risk a grim future. But here's the catch. We don't actually understand how changing environmental conditions will change the environment. You see, we know that plants are key contributors towards climate change. Volatile plant emissions, like the ones you smell when you walk into a forest, are powerful chemical compounds that can either contribute to or remove greenhouse gases from the air. This means that they can have both a warming and a cooling effect on the atmosphere. We also know that stress, such as that caused by drought and heat waves, can change these emissions, but what we don't yet understand is how or why. You see, as plants undergo stress, their physiology and thus their photosynthesis changes, and with that, so do their emissions. But we can't yet predict these changes, so they aren't included in current global climate models. Some of the better models use photosynthesis to scale up global emissions, but these aren't well constrained by actual plant studies. And that's because stress testing plants is very difficult. Most studies focus on a single stress factor, like drought alone, but this isn't representative of actual conditions where drought is often accompanied by increased temperatures. There's just too many parts to the plant climate feedback system and just too many missing experiments. But that's where I come in. I expose plants to single and combined stress, and I use a technique that I optimized to simultaneously measure both